Hello everyone, I'm Haowen Huang, a senior developer advocate at AWS. You are likely here because of the recent release of DeepSeek-R1, an advanced large language model, LLM, developed by DeepSeek, an emerging AI company headquartered in China. This is the first segment of a two-part series on DeepSeek. In this session, I will provide a technical overview of DeepSeek, covering its training pipeline, architecture optimizations, and infrastructure improvements. I will conclude this session with a preview of Part 2, where I will explore 4 methods for efficiently developing DeepSeek models on AWS. DeepSeek demonstrates how engineering innovations can achieve breakthroughs despite computational constraints. In the first part, I will examine DeepSeek's training pipeline, architecture design, and infrastructure optimizations to understand its internal workings. By understanding DeepSeek's underlying design principles, we will be better equipped to deploy it effectively and build upon its foundation to develop superior Gen AI applications that address real-world needs. Due to time limitation, we will cover the second part, deploying DeepSeek models on AWS, which is highlighted in gray in the agenda, in a separate follow-up session. Let's begin by explaining what DeepSeek is. DeepSeek is a new large language model, LLM, developed by a Chinese AI startup company. To date, DeepSeek has released several models under an open source and flexible license, including DeepSeek-R1. The company has published the R1 technical report, which presents benchmark results, showing that DeepSeek-R1's performance is comparable to OpenAI's GPT-4 model across various complex reasoning tasks. This achievement makes DeepSeek-R1 particularly significant, as it is the first open-source large language model to reach this level of performance. The DeepSeek-R1 model has become one of the most downloaded models on the Hugging Face platform. The model specialized in reasoning, mathematical computation, and coding tasks. Benchmark tests demonstrate that it performs comparable with OpenAI O1 while operating at roughly just 10% of the cost. Users can access these models through multiple ways on AWS, including Amazon Bedrock Marketplace, Amazon Bedrock's Import Models feature, and Amazon SageMaker Jumpstart, and other EC2 deployments. DeepSeek offers a suite of open-source models ranging from their flagship 671B parameter models to efficiently distilled variants. Their base models utilize diverse architectures and training methodologies, while the distilled versions are provided flexible deployment options. This variety allows organizations to select models that effectively balance computational requirements with performance capabilities for both edge computing and enterprise applications. Let's examine each of these models in detail. I will begin by introducing the DeepSeek V3 base model. DeepSeek V3 base is a decode-only transformer model, contains 671 billion parameters. trained on curated high-quality data, while V3-based incorporates several technical refinements. Its core architecture adheres to the standard decode-only transformer design, similar to models like Llama, Mixture, and GPT. The diagram on the right illustrates the training process of R1-Zero model, which was derived from V3-based through reinforced learning. During the reinforced learning process, the model receives positive reinforcement for accurate responses and negative reinforcement for incorrect ones. R1-Zero possesses a noteworthy capabilities. It demonstrates excellent performance in reasoning tasks without requiring supervised fine-tuning or SFT datasets. The model's training process begins with a pre-trained base model like DeepSeek V3 base and proceeds directly to reinforced learning. The left figure illustrates the increasing average response length of DeepSeek-R1-Zero throughout its training period. This trend indicates that the model gradually develops longer processing time when solving reasoning problems, leading to improved accuracy. The right figure reveals a aha moment during DeepSeek-R1-Zero's training process. This observation suggests that reinforced learning, or RL, may unlock novel cognitive capabilities in artificial systems, potentially enabling the development of more adaptable models. While DeepSeek-R1-Zero demonstrated robust reasoning capabilities, the model faced two significant issues. One, poor human readability. Since the model was trained primarily through reinforced learning without human supervised fine-tuning, its outputs were often difficult for humans to understand. And number two, language inconsistency. As the model frequently produced outputs that contains mixture language, especially combined Chinese and English within the same response. To address these issues, R1 was developed further using a four-stage training process. Stage 1 cold start, and Stage 2 reasoning-oriented reinforced learning. Stage 3 rejection sampling and supervised fine-tuning. The last stage, general-purpose reinforced learning. Through these four refined processes, DeepSeek-R1 achieved performance comparable to OpenAI O1, successfully balancing technical reasoning capabilities with general-purpose functionalities. After developing the R1 model, the DeepSeek team conducted research on knowledge distillation to transfer reasoning capabilities to smaller models. The distillation process involved using 800K samples generated by DeepSeek-R1 to fine-tune 6 different open-source models ranging from 1.5B to 70B parameters. This direct knowledge distillation method significantly improved the reasoning capabilities of smaller models, demonstrating R1's effectiveness in enhancing other models' performance. These findings reveal a straightforward optimization approach, generating training data from R1 and applying supervised fine-tuning to distillate smaller but highly capable models. Based on the previous introduction, we have covered the basics of DeepSeek model series and its training pipeline. Now, let's examine the DeepSeek model's innovations and optimizations in two key areas: architectural optimization and infrastructure optimization. DeepSeek's models feature several key innovations and technical optimizations. This discussion will focus on 5 primary optimizations: multi-level attention (MLA), DeepSeek-MoE, multi-token prediction (MTP), DualPipe, and FP8 Training. These optimizations fall into 2 main categories: architecture and infrastructure. DeepSeek's optimization strategy is built on 3 fundamental engineering principles. Number 1, meticulous optimization. And number 2, core design integration. And number 3, strategic trade-offs. Let's examine each of these 5 optimizations in detail. To help everyone gain a high-level understanding of the main optimizations and innovations in the DeepSeek model, I have specifically mapped 3 key optimization points to their corresponding components in the transformer architecture. MLA, multi-head latent attention, and DeepSeek-MoE was already implemented in DeepSeek-V2 model, and they are not innovations of the V3 model. The innovative idea of multi-token prediction (MTP) comes from DeepSeek-V3 model. Next, let's introduce these 3 main optimization points one by one. To better understand MLA, let me first explain the background of large language model inference. During LLM inference, key value or KV catching operations are performed where the system catches the components indicated by the orange dashed box in the upper portion of the diagram. When input prompts share the similarities, the system can query the existing KV cache instead of recalculating all the values, thereby saving computational resources at the cost of memory usage. MLA implements low-rank joint compression, a technique that introduced a latent layer shown in the origin dashed section at the bottom of the diagram. The compression produces significant benefits. The dimensionality of the vector representation is reduced from the original 128 by 128 dimensions to just 512 dimensions. This means that the high-dimensional vector is effectively compressed into a more compact representation, substantially reducing memory requirements during KV cache operation. There's another important engineering design consideration here. While compression does lead to some performance degradation, good trade-offs can be made to minimize the noticeable impact. As shown in the red dotted section on the left, compression was also applied to the Q part of the transformer, but to a lesser degree. You see just 1,536 dimensions compared to the KV compression at 512 dimensions on the right. So for Q part on the left, the researchers chosen a lower compression ratio. From the overview of the MLA optimization, we can see that DeepSeek researchers were very meticulous in their architecture optimization, ensuring that while compression was applied, the performance loss was minimal. This attention to detail in engineering optimization is actually present throughout the entire evolution and design of the DeepSeek model series. DeepSeek optimized the mixture of experts MOE architecture by implementing a more fine-grained expert structure. Unlike traditional MOE, DeepSeek MOE reduces parameters per expert while increasing expert count. While mixture uses 8 experts, DeepSeek uses 256. DeepSeek splits experts into shared experts and routed experts, each with distinct processing workflows. Shared experts process input data directly, bypassing the routing module. Routed experts receive input through a routing module that selects experts based on input features. This module calculates probability scores between inputs and experts, choosing those with highest matches. The outputs from both expert types are combined for the final MOE output. This design captures both common patterns and unique features in data, improve the model generalization and adaptability. Another notable engineering optimization is DeepSeek MOE is node-limited routing. Node-limited routing ensures that each token is sent to at most m nodes. Since input tokens and experts may reside on different GPUs, cross-node communication can become a bottleneck in the training system. As shown in the diagram, limitation to routable nodes to 4 can further improve training efficiency. DeepSeek MOE includes several other excellent engineering optimizations. Due to time constraints, I won't elaborate on all of them here. For those interested in learning more about DeepSeek MOE, please refer to the DeepSeek V3 technical report, which provides more detailed information. The DeepSeek V3 technical report highlights V3 sets a multi-token prediction training objective for stronger performance as a key innovation. Let's explore MTP, multi-token prediction. Currently, autoregressive language models use single-token prediction, predicting the next likely token based on the context. MTP instead predicts multiple tokens at once, improve efficiency, quality, and speed. The benefits are clear. Generating multiple tokens at once reduces generating steppers and speed up inference. During training, MTP's objective function evaluates multi-token predictions together, capturing token dependencies and improve performance. And GRPO, which is Group Relative Policy Optimization, represents an innovation that replaced the traditional PPO algorithm by eliminating the value model component. Traditional PPO implementations utilize both value and reward models in their architecture. To illustrate the distinction between value and reward models, considering the analogy of sharpening an axe before cutting wood. A dull axe cuts one piece of wood per minute, while a sharp axe cuts 2. The choice is between immediate use the dull axe or investing maybe some time in sharpening it first. So immediate cutting produces higher short-term returns but lower long-term efficiency. The value model, like the decision to sharpen the axe, prioritizes long-term benefits, while the reward model, like immediate cutting, emphasizes short-term returns. while PPO effectively improved model response in RLHF, which is reinforced learning from human feedback, it faced challenges with computational overhead and training stability. But GRPO addresses these challenges by eliminating the value model, resulting in a nearly 50% reduction in training resources requirements while maintaining performance. Having reviewed the architectural innovations and the optimizations of the DeepSeek model, we will now explore the infrastructure-related optimizations. The first infrastructure-level optimization I want to highlight is DualPipe, a level bidirectional pipeline scheduling mechanism designed to enhance computational efficiency in GPU clusters during model training. The fundamental challenge in large language model training stems from the fact that large-scale models exceed the memory capacity of a single GPU, requiring model parallelism across multiple GPUs. This distributed architecture requires multiple nodes to operate in coordination. However, during computation, inefficiencies arise when some nodes remain idle, creating what are known as bubbles due to varying computational workloads and inter-node dependencies. Maximizing GPU's resource utilization has thus emerged as a critical challenge in the field. As illustrated in this slide, DeepSeek addresses these challenges through bidirectional pipe scheduling, which enables concurrent processing of macro batches from both ends of the pipeline. This approach significantly reduces the idle time, which is bubbles, at the training's initialization phase and enhances overall GPU utilization efficiency. This implementation represents a significant engineering advances in DeepSeek's pipeline parallel distributed computing architecture. Regarding the bubbles that appear during training, DeepSeek described their improvement method in their technical report, which they called efficiency overlapping strategy. As shown on this slide in the image above, the yellow parts represent forward computation and the blue part represent backward computation. DeepSeek's new design divided the computation in each direction into 4 smaller parts. Attention means representing multi-head attention computation. Dispatch represents distributing information to node prepared for MOE computation. And MLP represents model parallel MOE, which is DeepSeek-MOE. Combine represents merging information after MOE computation. Why they do this? Because after breaking it down into smaller parts, the computations are interleaved, making the entire process more compact. We can use Tetris as a more vivid analogy. In Tetris, if you want to fill all the spaces as much as possible, you need components of different shapes, right? DeepSeek's DualPipe can be compared to innovating different shaped components, allowing for better space filling. In summary, the DualPipe innovation enables DeepSeek to achieve efficient, large-scale model training under limited resource conditions. Another infrastructure-level optimization is FP8 training, which is a kind of mixtured precision framework training. DeepSeek V3 model uses FP8 training to enhance training stability and maintain training effectiveness without significant degradation, the DeepSeek team proposed a refined quantization strategy. Additionally, to further reduce memory and communication overhead in MoE training, activation values are cached and distributed in FP8, while optimizer states are still stored in BF16 format. The training framework maintains original precision such as BF16 or FP32 in the following components: embedding modules, output heads, MoE gating module, normalization operators, and attention operators. These high-precision preservations ensure stable training dynamics for DeepSeek-V3. Considering the DualPipe and FP8 training that we have discussed, these are all engineering optimization from DeepSeek, which provide practical guidance for the optimization of large language model training. Let's summarize what we were covered so far. In this part 1, we explored DeepSeek's major engineering innovation across 3 areas: training pipeline, architecture optimization, and infrastructure optimization. These groundbreaking approaches have helped overcome computational constraints in remarkable ways. In the upcoming part 2, I will focus on efficient deployment strategies for DeepSeek models on AWS. I will introduce 4 different methods. Each deployment approach has its unique use cases and advantages, which will help developers make smart decisions for efficiently deploying DeepSeek models on AWS. So please stay tuned. Before ending this session, one final call to action for you is to create AWS Builder ID profile. If you haven't created that already, you should. First and foremost, you will be able to reserve your username. Also, you will get access to resources like AWS Skill Builder, AWS Repost, and you will be able to connect your profile with AWS training and certification, but also to the tools like Amazon Q Developer. Last but not least, you will be among the first to explore many new AWS offerings. And this concludes the first part of my presentation. I regularly shared my latest blog posts and videos about generative AI and large language models on my LinkedIn profile and YouTube channel. I invite you to follow my LinkedIn profile or subscribe to my YouTube channel so we can exchange ideas and experience as fellow large language model technology fans. In part 2, I will demonstrate step-by-step procedures for efficiently deploying DeepSeek models on AWS. Thank you for your attention, and I look forward to seeing you in next session.